We're going to introduce logarithms now. And to motivate our need for logarithms, let's take a look at an application question that we might want to be able to answer. In fact, this is a preview of a typical kind of question we will be answering later on in the course. Suppose we have an exponential function, like the one we've seen before, for describing the balance of a bank account earning compound interest. So for example, this function describes a bank account that starts with $500 and earns 1% interest each month. And imagine we want to know how long it will take for the balance to reach $600, starting from $500, earning 1% interest compounded each month. Well, what we can do is take the formula for our balance and set it equal to 600, and then algebraically try to solve for the variable t. So the first thing you would do with this equation is divide both sides by 500, and you can simplify that some more. On the right side, 600 divided by 500 is just 1.2. And now you want to isolate t here, but basically what we're trying to answer is the following question. What power of 1.01 do we need in order to get 1.2? So that's the type of question that logarithms answer for us. What power of a given value do we need to get another value? The number we're raising to a power is referred to as the base of the logarithm. So for example, if I say the logarithm base 2 of 8, I'm asking what power of 2 do I need to get 8? And of course the right answer is 3. If I take 2 and raise it to the power 3, I get 8. So we can express this relationship by saying that the logarithm base 2 is 8, and that's written this way. Log, short for logarithm. Base 2 is indicated as a subscript here. And we're asking, when we look at this, what power of 2 do we need to get 8? The power we need is 3, so the quantity on the left side is just equal to 3. Let's look at a few more examples. Imagine I write down logarithm base 10 of 100. What I'm really asking is, what power of 10 do I need to get 100? And of course the answer is 2, because if I take 10 and raise it to the power 2, I get 100. What if I ask, what's the logarithm base 10 of 10? Well, that's just 1, because that's the power of this 10 I need to get this 10. How about the logarithm base 4 of 2? Well, that's a half. And the reason is 1/2 is the right power of 4 to get 2. Remember that a 1/2 power is another way of expressing a square root. So 4 to the 1/2 is the same as 2. Finally, what if I want the logarithm base 10 of 0.1? Well, that value is -1, and the reason is a -1 exponent is the right power of 10, because a -1 exponent gives me a reciprocal, and a reciprocal 1/10 is the same as 0.1. So the power of 10 I need to get 0.1 is -1. So we can see that there are two different ways of expressing the relationship between values when there's an exponential relationship. Like if I say that b raised to the power a equals c. Another way of thinking of that is a is the power of b you need to get c. So the power of b you need to get c is a. So you can express the relationship either in this form or in this form, and they mean exactly the same thing. The first form is called the exponential form of the relationship between these numbers. The second form is called the logarithmic form. It's useful to be able to go back and forth between those forms when we're trying to answer questions like this one. Let's write this equation, log base 7 of x equals 9, in exponential form. So what does that mean? Well, this is saying the power of 7 you need to get x happens to be 9. 9 is the power of 7 that gives you x. So, if I make 9 a power of 7, I'll get x. And that's it. This is the exponential form of the relationship. It's the exponential form of this equation. For another example, let's go the other way. Let's start with something in exponential form and write it in logarithmic form. This equation, 2 to the y equals 10, means y is the power of 2 that gives me 10. The power of 2 that gives me 10. Well, that's logarithm base 2 of 10. So this is the logarithmic form of this exponential equation. This is a useful way of thinking about a problem when we're trying to evaluate a logarithm by hand. If I want to evaluate, for example, log base 3 of 27, I'm really asking what power of 3 will give me 27. So you could imagine trying different numbers here. Maybe you could try a 2, but that doesn't work. 3 squared doesn't give you 27, it gives you 9. 3 to the 3 works. 3 cubed is 27. So the correct exponent of 3 is 3. So the power of 3 you need to get 27, the right thing to go in this box is 3. Let's evaluate log base 4 of 1/16. Thinking of this as an exponential relationship, we're asking what power of 4 gives us 1/16. And let's say you try 4 squared. You try putting a 2 in this box. That doesn't work. It gives you 16, not 1/16. But we're close. We're on the right track. Because although I don't want 16, all I want is the reciprocal of 16. And I can get a reciprocal out of an exponent by using a negative exponent. So if I fill in this box with a -2, I'll get the right value, which means -2 is the power of 4 I need to get 1/16. So -2 is the logarithm base 4 of 1/16. Now, there are a lot of values that are not as easy to compute by hand. Let's look at an example of how we might do this on a calculator. If you want to take a logarithm base 10, most calculators have a button that makes that easy to do. Base 10 is used very often, so often that it's actually got a nickname. It's called the common logarithm. So let's see how we could apply this technique for evaluating log base 10 on a calculator, and we'll learn how to evaluate logarithms with other bases later on. Suppose we want log base 10 of 250. So if we take a look at the calculator, on this TI-84, on the left-hand side, the fourth button from the bottom, LOG, that's short for logarithm. And if I press that button, the calculator is asking me what value to take a logarithm of. And I'm going to be taking a logarithm of 250, so let's type that in and hit enter to evaluate. And the calculator gave us 2.3979, so approximately 2.4. Notice that I never said what the base was. That's because when I use the LOG log button, it's assuming base 10. It's the common logarithm button. So based on what we got on the calculator here, the right answer is approximately 2.4. Now, whenever we use the calculator and we use that LOG button, we're assuming base 10. And just like the calculator did, it didn't write a base, and sometimes we'll do that too. If we just write log of 250, that's shorthand for log base 10. If you leave out the base, like we did here, then you're really saying that it's base 10. There's another base that's also really important in mathematics, especially when we get to calculus, base E. Remember, E is Euler's number. It's approximately 2.718. And just like we can use a calculator to evaluate expressions involving Euler's number, there's also a button for evaluating logarithms, base Euler's number, base E. There's also special notation. Log base E can be written as ln. That's the shorthand for log base E. This is called the natural logarithm, and we can evaluate it on the calculator by pressing the ln button. So if I want natural log of 30, I just type ln of 30, close the parentheses, hit enter, and I can see from this that the answer is approximately 3.4.